Right. So it is 9:30 and we should start. And if you know anyone that is not here today, please tell them, make sure they need to watch this lecture. This lecture is one of the most important topics of the course, and that is sequential logic timing. Sequential logic timing is very critical for making sure that our designs are correct and predictable. And your quiz, not this upcoming one in 2 weeks, but the one after that will probably be on sequential logic timing. And if it's so basically, if it's not the one in 2 weeks, it's the one after that. But for sure, you will have a quiz on sequential logic timing. You will need to know this. All right. So timing constraints and sequential designs. So if our timing is incorrect, our logically correct design can go wrong. And we need to make sure that the timing is the timing equations are satisfied, because if they are not satisfied, we will get unpredictable behavior from our circuits and incorrect results. So before we can go into sequential logic timing, we have to review a little bit about the combinational logic timing, because in our sequential circuits, we have combinational parts in it. So the combinational logic timing, the minimum delay of a gate is also called the contamination delay, right? You'll see this as TCD. And it's the minimum time from when an input changes on the gate to when the output starts to change. And then the maximum delay of a gate, this is also called propagation delay. This will be seen as TPD. This is the maximum time from when an input changes until the output is guaranteed to reach its final value, as in is done changing. So we have these two different timing characteristics of combinational logic circuits. We have the minimum, which is contamination, and the maximum, which is propagation, right? So here is our little review. Let's not do this question as the poll. So which path in the above circuit determines the contamination delay of the circuits, assuming the delay of all the gates is the same? Which path is the contamination delay? Yeah, D. So it'd be the red path, which would be B in terms of the answer, right? Because it's only going through one gate. So it's the minimum time between one of the inputs changes that the output starts to change. So if D changes, the output will start to change. If this NOR gate evaluates to a different value than what Y currently is. So it is B, the red path. And then the path that determines the propagation delay of this circuit is A, right? We're going through 1, 2, 3 gates. So if A or B changes, then it's going to start changing here, and then it starts changing here, and then it starts changing here. So it can take a lot more time than if C or D changes for the outputs, right? So again, contamination is the minimum delay, propagation is the maximum delay, right? All right, so going beyond the combinational logic timing, we have to talk about the timing of our D flip-flops. So there are these two variables in our D flip-flops. The first one is the setup time. This is the time before the clock edge that the data must be stable. it cannot change during the setup time. If it changes during the setup time, then the value that is latched on by the first latch is most likely not your correct value that you wanted. And this setup time is basically the time that it takes for D to reach through to Q on that first latch. Because we're saying that we need the input D to be stable and not change for at least the time it takes for the input to pass through and get saved into the latch. Because if we do not have our D stable before then, the latch will not latch on to this new value. Yes. Remember, I told you not to do that one, right? Or are you talking about test benches?
Well, in the file, in the main PHP file, we put, so we have any fade until we say after 2 nanoseconds, right?
Remember, I said not to do that.
Mark told us to.
Well, don't do that.
I think we needed it for the very first one.
You don't need it.
Okay.
You should not need that.
If you didn't use it, you could put something in your constraint file and say a clock thing.
Yes. Yes, and that's how you can get it to work on the board.
Oh, we ended up doing that. Okay, so we
Yeah.
can, once we do that, we can take that to nanoseconds out.
Yes.
Okay. That's.
Okay. Yes.
Is it just us monitoring the outputs later, or is something, some component or something usually checked to make sure the clock is stable
You
or the output is stable before it?
So there are algorithms that use the equation that I'm going to go over to tell you if your timing constraints are met or not.
Okay.
But is it clear for you guys why you need this setup time? Because you need to be able to propagate that signal through into this first latch. If it never propagates through to this first latch, it's not going to be saved into the first latch at pause edge clock. Right?
That causes the result to be undefined.
It will cause the results to be the previous result rather than the new updated result.
Which is undefined.
If it was undefined before, it would stay undefined. If it was 0 and it needed to change to 1, it would be 0. Yes.
Would we do this in the test bench? Or does Vivado automatically just assume?
Vivado will do this timing constraint for you, but you need to be aware of it so that you can understand how to maximize your performance. All right, so is setup time clear? Yes. D cannot change during setup. Yeah, when it's trying to latch. So because if D is changing, well, we are going to latch onto the value, then it could be undefined or it could just not propagate through the latch. So we latch onto the previous value rather than the new value. So we need to make sure that our new inputs is stable and not changing before this setup time before the clock edge, the pause edge. Are we good with that? Okay. The other thing, the second part, hold time. So this is the time after the clock edge that the data must still be stable. And this is because when the clock changes from 0 to 1, this latch is turning off, right? Disabling. And this one is enabling, right? But it does not happen instantaneously, right? There is some time that it takes for these AND gates to evaluate the clock change, right? And that is the time that we need to make sure that D is held. Because if it changes during that time to a new value, then the new value might make its way through to the latch. Yes.
So instead of the clock signal automatically going up, down, you would have like a line, right?
Yes. It's not instantaneous. So that's what this whole time is for. So it's not just the clock that takes time, but after the clock changes, these AND gates also need to evaluate. So that's what the whole time is for. So setup time, if you have a violation, you could keep your previous value that you didn't want to keep. Hold time, if you have a violation, you can skip a value that you were not trying to skip. So if we look at a flip-flop, we are also having these timing characteristics. So this is, the first one is the minimum delay of the flip-flop is the contamination delay. And we are calling this TCCQ. So it's the clock to contamination clock to Q. So this is the time after the clock edge that Q might be unstable. It's still changing. Okay. And then we have the maximum delay of a flip-flop. And this is the propagation delay, right? And this is T propagation clock to Q, TPCQ. So this is the time after the clock edge that output Q is guaranteed to be stable. So here are our two things, right? So the clock edge happens. How long before the output starts to change? And then how long until the output is stable with the new change? Yes.
So these are all the bounds that we need to be able to optimize.
I have not shown you the bounds.
Okay.
I've just, I'm only explaining the different variables that go along into the equation so far. All right. So this one, again, let's do this together because you have other questions that we should go over. The timing of which of the following signals can cause a setup time violation? So setup time occurs when? So on which part? So it's the input, DFT. The timing from here to here is what we are concerned with for our setup.
Your
Yeah,
mouse wasn't shown on our screen now.
I'm moving it.
There we go.
The timing from here to here is what we need to concern ourselves with for our timing constraints. All right, so this one I do want you to work on your own first. Your code for today is 209. So we have an input into a flip-flop coming from the output of another flip-flop, and it goes through a combinational circuit first. The flip-flop and combinational circuit have a minimum and maximum delay. The question is, which of the following violations occurs if the max delay of R1, so this flip-flop, is 0, and the max delay of the combinational circuit is equal to the clock period? So propagation delay is from here to here. Is anyone still thinking about this on their own? I didn't see any new answers coming in. All right. We are very close to the threshold, but we are not quite there. So do talk to the people around you and discuss how you got to your answer. Actually comes my name. You can go
I'm an autopilot.
Believeme.com/professor.
You like the way you
The what? Oh.
Maybe it might be set up. You see that the time is zero. Just
Wait, you said it.
I think so.
Okay, if you were convinced to change your answer, do change your answer. All right, let's go through this. Okay. So we're saying that the maximum delay of R1, and what is this? T PCQ, right? Propagation delay from clock to Q of R1 is 0. And that is represented by here, right? Clock to Q, this arrow. So we're saying this is 0, right? And then the maximum delay of the combinational circuits is equal to the clock period. So that's the propagation delay, or TPD, of this combinational logic, right? And that would be represented by this arrow. But we're saying that this arrow is really the same amount of time as this whole clock period, right? So then what do we need to ensure before the clock edge? Stable input before setup time, right? R2 has this setup time constraint, right? But if the combinational logic plus the delay of the register takes up the whole period, then it's not guaranteed that my input is stable before the setup time. So we have B, a setup time violation for R2. Yes.
Are we assuming R1 has?
Yeah, but we're not concerned with it because it's not shown here. What is on the input to R1, right? We're only looking at the timing for R2. We have from one register to one register. So here is our setup time constraint. We have that the clock period needs to be greater than or equal to the setup time plus the delay of the flip-flop that the signal is coming out of, plus the delay of the combinational circuit part. And if you wanted to order it in the way that it would occur in real time, the first thing that happens is propagation clock to Q from the first register. The second thing that happens is propagation delay of the combinational circuit once it sees that change from the register to where it's stable, right? And then we have the setup time. So the time needed before the clock edge or the next register in order to capture the input properly. So this is your setup time constraint for registers. Yes.
And this is all on the scale of like nanoseconds.
Usually, yes. It could be microseconds though. Like for an FPGA, it's usually in the microseconds because we're in megahertz clocks. But for a CPU, you're in gigahertz, so that would be nanoseconds. All right. So the next question, again, do this one on your own. The setup is very similar, except now, which of the violations would occur if the minimum delay of R1 is 0 and the combinational circuit is just a wire? If it's just a wire, what does that mean its delay is? 0, right? Okay, is anyone still thinking about this individually? Let's see. We are not close to the threshold this time. So I'll tell you 18% of the respondents have the right answer. So try and discuss with each other and think about which one has the violation, what is the violation, right? So that's your hint, it's not E, right? There is a violation.
So the first thing is this is zero. You don't give them
It's set up for our.
I see.
Because R1 could.
Oh, I see. Okay. That's it. I mean, sorry, Justin. In our Vivado test bench files, if we zoom in on the clock, would that just be a line?
Because that's functional simulation and not real simulation, it's a square. In reality, it's this curve.
Yeah.
But it does happen really fast. Okay, do change your answer if you were convinced to change your answer. All right, so the positive thing is we understand that what kind of violation this is. There's just a misunderstanding of where the violation is occurring. So when we're saying that there's a violation, we're talking about where does the error occur. So just because the error is coming from the output of R1 and through this combinational logic, but the error actually occurs that R2 skips. It's the input that it should have captured. So that's why when we're looking at both of these, like with the setup, it doesn't capture the input in time, so it keeps the old one. So that's why the violation for setup here is on R2. And this one, it's skipping. And that's why this one is also hold time violation for R2. Because if you have no delay between R1 and R2, so being the contamination clock to Q and the contamination of the combinational logic, then what happens is the input before, say it was stable, right? It didn't violate setup time. Then when the latch here is trying to disable, right? If there's no delay from here to here, the next input is immediately trying to change what this first latch is trying to latch onto. That's how it can skip the input. Yes.
So we're saying that R1 delay is zero, wouldn't that be a violation itself because you wouldn't give it enough time to give it one to begin with?
So R1 delay being zero is just saying that from clock to Q, it takes 0 time. It has nothing to do with is R1 capturing its value correctly. But the hold time over here you need to make sure that you're holding the input for a certain amount of time after the clock to ensure that the first latch is disabled and capturing the input that it should be capturing. So that's just to be clear that when we're talking about a violation on a register, we're talking about the register where the violation or the error occurs. So where it occurs. All right, so this is our hold time constraint. So basically our hold time needs to be less than the time that it takes to go from clock to queue of the other register plus the contamination delay. Because if it's less than this, then the inputs will for sure be stable longer than hold because it takes too long for the signal to propagate in order to contaminate. Does that make sense? Okay, so these are our two equations. We need to satisfy setup time to ensure that our clock period is long enough so that we can have a stable input before the next clock edge. And then this, you need to ensure that your combinational logic and your register delay is long enough so that it doesn't change the input right after the clock edge too fast. So here we have our flip-flops, and they have these characteristics. So we need the setup time, the time that it's needed to set up, the hold time, the time that is needed after the clock edge to ensure that it captures the input properly, and then the delay, the contamination delay from clock to queue, propagation delay clock to queue. Okay. So then the other thing that is going to go into these equations is these clocks are the same signal, right? And they're coming from the same source, but these registers are physically in different places, right? So yes, a wire is very, very fast, but there is still some delay added with wires. Yes? So these clock edges do not actually arrive at the exact same time, right? So this is what we call clock skew. So it's the difference between the two clock edges. And when we do a timing analysis with considering clock skew, because again, the clock, even though it's the same clock, there's a delay between them. One can arrive early, one can arrive late, and it can vary each time for every cycle. So we call that skew. So if we go to our equations, again, we do a worst case analysis. So in the worst case, for a setup violation, the clock comes early, right? So in that case, it means that we need to make sure that our clock period is long enough to accommodate the earliest possible early clock edge. So we add the skew to this equation, right? But then if we have the hold time constraint, again, we're doing worst case analysis here. for a hold violation, the problem occurs if the clock is late, right? Because if the clock is late, that means that I actually need to hold for longer than expected. So that's why if we look at it here, we are subtracting rather than adding.
Basically added at the beginning, then before we get to the whole time, subtract it to make sure it's equal.
No,
See?
these are two different equations, right? So this one, the problem is if the clock is early. So if it's early, that means I have less time to propagate my signal through. But here, if it's late, that means I require more time to hold the correct value. That's why one was added, one was subtracted. And this clock skew, it's often also called clock jitter, is usually given as a percentage of the total cycle time. So if your clock period is 100 nanoseconds and it says you have a clock skew of 5%, that means that the maximum real clock period that you will ever see is 105 nanoseconds. And the minimum real clock period you'll see is 95 nanoseconds. So it varies. Right? So that's why you have to include that here. So here is our timing analysis example. We have these 4 registers, A, B, C, D, and we have 2 output registers, X and Y. And we need to do our 2 equations, right? We have setup time. So our clock period needs to be greater than the first value is the propagation clock to Q, right? That comes right straight from our characteristics of the flip-flops. So it's 50 picoseconds. And then the propagation delay of this combinational circuit, we have to do that analysis, right? So it's going through this AND gate, an OR gate, and a NOR gate, and we're saying that every gate is the same propagation and contamination. So that means that's the longest time is from A to Y or B to Y through 3 gates, right? So propagation delay of the combinational part is 105 picoseconds. So that's where this 105 comes from. That's our TPD. And then we have finally the setup time, because we have to be finished before setup time before the clock edge, right? So that means our period needs to be greater than or equal to this equation, right? Which is 215 picoseconds. And if you wanted to convert that to frequency, it would be 4.65 gigahertz. And the second thing that we need to ensure is that our hold time constraint is also satisfied. So our hold time, we have to make sure that the contamination clock to Q and the contamination delay of the combinational logic is greater than the hold time, right? So if we look at our contamination clock to Q, 30, and then our contamination delay of the combinational circuit is from D to Y, 1 gate. 1 gate is 25 picoseconds. So 30 plus 25 gets me 55 picoseconds. And if I put in the hold time for the flip-flops, it's supposed to be 70 picoseconds. So it's possible that I have a hold time violation, right? If the input D changes and it's going to change the output y, then that's when my violation would occur. So this one is not satisfied. So how can we fix this? Yeah, a buffer. We need buffers. So it doesn't affect the overall time because we need to have a longer clock period anyways in order to satisfy the case of the propagation delay of the longest one, right? So by adding these buffers, our performance is not impacted. But we are now satisfying the hold time because now it's 1, 2, and 1, 2. So we have 2 gate delay, so 50, and then 50 plus 30 from our contamination clock to Q. This is 80, that's greater than 70. So it is possible that adding these buffers will require you to impact your performance in terms of your cycle time, but in this case, it did not impact it. And we just now have a correct circuit for all input combinations. So that's how you can fix it. And your quiz will look something like this. You'll be given some registers, some combinational logic in between registers. And I want you to tell me if there's a setup time violation, hold time violation, or I can ask you what is the minimum clock period of the circuits, things like that. And we will do some practice next week. But before we go into more practice on the timing analysis equations for sequential logic circuits, we are first going to learn about finite state machines. So finite state machines are going to be the first kind of higher level application of digital logic circuits that you're going to learn about. So rather than just going from truth tables to the digital logic circuits and why am I doing these truth tables, you'll see what kind of real applications you can make with finite state machines. That's underneath them, they have these truth tables still, right? Because we want to minimize those logic circuits. That's where the truth tables come in and the K-maps come in, right? So that is it for today. Do finish and turn in lab 4. Again, there is reading for Monday. Book 3, chapter 1.1 through 4, you'll read about finite state machines. Okay.